Hello everybody and welcome to the NPTEL online course on microelectronics devices to circuits. We start today's lecture with the understanding of BJT as a switch and then conclude with Ebers Moll model of BJT. I will also give you a brief introduction of Gamal-Poon model, which is generally used in SPICE for SPICE purposes, which is a circuit simulator. But before we move forward, let me recapitulate what we did earlier. We had a look into the various small signal models available to us, out of which we had conclusively looked into common emitter, common base and common collector configuration. We have also seen in common emitter, if we put a emitter resistance in series to the emitter port, it increases the stability and decreases the gain. So, that is what we have done in the previous lectures. We will start today to look into BJT as a switch and then maybe look into Ebers Moll model at a later time, right. So, just to the outline of this presentation or this set of presentations will be that we will be looking BJT as a switch. So, can we use BJT for the purpose of switch, right, and the requirement is that whenever we have switched networks, can we use BJT to do that, right, or can we use BJT to take care of those switch networks. We will be looking at Ebers Moll model and its equations. So, again as I discussed with you that small signal model and it is basically a circuit simulation model, and therefore, we will be able to directly port these equations into circuits for the purpose of circuit simulation. Then we will be looking at normal mode of operation of transistor, which we have already seen, and then the inverse mode, and then we will be putting the Ebers Moll model for NPN as well as PNP transistor, and then recapitulate the whole thing once again, which means that we will be looking into these detailed analysis once again. Now, we will be looking first of all BJT as a switch, right, that is the first assignment or the first part in this idea, and they have been used for all your transistor logic, which is basically TTL. So, let us see how BJT can work as a switch. Now, so we remember, if we just now discussed and we saw that when the base emitter voltage goes beyond 0.7, which is basically for silicon, then we would expect to see it become forward biased, and as a result it will emit large number of electrons if it is an NPN transistor, and the device will be in on state, right, and it will be in off state provided the base to emitter voltage is lower than 0.7 as such. So, if you are able to make a transition of the base to emitter voltage from 0.7 upwards to below, I can move from saturation to cutoff and vice versa. Consider this circuit which you see in front of you, this circuit, right, where I am giving an input voltage Vi, right. So, this means that we are giving a input voltage which is Vi, and this will be a sum of DC and AC bias. So, the DC bias will be helpful for choosing the Q point, and the AC bias will be actually giving you the switching characteristics. So, whenever this RB and RC, this RB and this RC are the resistance which is there in the base side and the collector side of this BJT. They are there so that excessive current does not flow through BJT and burn it out. So, if let us suppose this got shorted, RB was shorted, then if your source which is a voltage source, a DC voltage source, because of some problem or other gives you a large current suddenly, then the chances are that the BJT will burn out, and therefore, in order to ensure that it does not burn out, we give a RB value here. So, this RB, RC and the beta of the transistor fixes up the Q point of the transistor. So, it gives me a fixed value of VCE and IC, right, it gives me that value. Where should you bias so that it acts as a switch, that we need to find out how do you bias it. So, if you plot in a common emitter configuration for various values of VCE versus IC, if you plot, right, then for this is for various values of IB, I think, right. So, this is IB1, IB2 and so on and so forth, IB4, IB3, and this is basically IC and this is your VCE. So, this becomes your IC4, right. This becomes your IC3, this becomes your IC2, and this becomes your IC1. So, this is your saturation region almost, and this is your active region. Active region, this is your saturation region. So, you have another, suppose you have a current source which is somewhere here. So, typically for to be used as a switch, if you bias it somewhere here, let us suppose, which we generally do if you are using it as an amplifier, suppose use the Q point, then you are, so if you look at the Q point, then I will just give you the region. So, this is the, so this is your, let me show you using a different color maybe, and I will just show you the different color combination, and maybe let me use this. Now, this part, right, this part which you see, as I discussed with you, is basically your saturation, right. Now, this part, right, is your, sorry, this part is your active, this is active, and below this part, this is all cut off, and this IB is approximately equals to 0 or very close to 0. So, if you bias your device in such a manner that you end up having your Q point is somewhere here, then you can understand that even if I give a small signal input, I will not be able to cross the cutoff point. So, at the positive half cycle there is surely no reason. Negative half cycle also, my IB will just come from IB4 to IB2. So, if you bias your device at this Q point, you will never be able to work as a switch, but then you can work as an good amplifier. So, the good idea is that if you want to use it as an amplifier, bias is by using external DC sources in such a manner that it is somewhere in the middle of the active region, not very far from saturation is cut off. You want to use it as a switch, then bias it somewhere maybe here or maybe somewhere here. Then in the positive half cycle, agree, nothing will happen, but the negative half cycle you enter into cutoff, right. So, when your input is moving in the negative half cycle, the output is also going to the negative half cycle, then you are entering into cutoff limit, right. So, you can do cutoff. So, but to do that, you have to your VCE may be typically large, but then you need to ensure your IC to be small. So, this IC is a small IC. This small IC can only be done if you have IB small. How do you do that? IB, how can you make your IB go very small? Well, very simple and straightforward. If you look at this point, make your RB very large. So, when you make it RB very large, you ensure that your IB falls down drastically, right, and then as a result you will have a much lower value of RB, much lower value of IB available with you. As a result, you will be able to go into cutoff. Now, the idea therefore is that when you go from therefore active to cutoff, right, without going into saturation, we define that to be as a switch, right. So, we define switch to be from active to cut off, right, and then vice versa. So, from cut off to active again you want to go to it. Now, you will obvious question asked is can BJT be used for high frequency application, which means that can I use this switch when the input frequency is typically very high? The answer is it's difficult, it's pretty difficult, and the reason being that how does one go from on to off state? We go via changing the emitter base junction from forward to reverse bias and then from reverse to forward. Now, there is always a finite amount of time which has to be given to the diode, PN junction diode in this case, such that you allow for the systems or the charge carriers to come back to its original position. This is known as reverse recovery time, right. We will not discuss any further than this at this stage, but I will give you a brief idea what I was talking about. So, let us suppose I have a PN junction, right. So, assume this to be as emitter and this to be as base. So, I have got NPN. So, this is N and this is P, let us suppose I have a depletion region here. Now, what I do is I first of all I first of all forward bias it. So, I do like this. As I do it, current flows and there is no problem. Then what I do, I have to reverse bias it. So, what I do, I just remove this part and I add something like this. Once I reverse bias it, this again the current stops, because the depletion thickness becomes quite large and there is no current. Then we again go from reverse to forward, right. Once I do it, then this has to go down, this limit has to go down. How it can go down? Provided the charge carriers from both sides move across the boundary, meteorological boundary, and thereby form the remove the depletion region. This requires a finite amount of time, and that is the reason you have to give sort of a minimum cooling period for the diode, so that it basically moves from on to off state and off to on state. So, typically BJTs cannot, for this simple reason, there are other reasons also, but this is one of the reasons why you cannot work it at a very high frequency, right, at typically gigahertz or terahertz you cannot work with BJT. The reason is you do have a problem that a minimum amount of time has to be given to the transistor in for the BJT for the recovery of the time, right. So, that is the reason there is always a limit to the frequency at which the BJT can work as a switch. So, if you look at this figure or in this equations, you can see that IB, the base current, can be given as VI, VI is the input voltage, minus VBE. Minus VBE, why? Because this is the, so I am concentrating at this place, right. So, it is something like this now, that I have RB, right, and then this, right, and then you have got VI. So, VI minus VBE, right, minus VBE divided by RB is your IB. So, this is your IB, right. So, IC will be equals to beta times IB, with straightforward way of looking at it, and therefore, if you multiply this IC with RC, and then VC will be equals to VCC minus IC RC, and I will get from this equation the value of VC, which is the collector voltage available with me. Therefore, as you can remember, IC SAT, from here also you can see IC SAT will be equals to VCC minus VCE SAT by RC. Now, I will ask you where is this SAT or from where I can get the SAT value. Remember, if you remember the voltage transfer characteristics which we are studying, right, and we were studying like this, and then it was going like this, and we defined this to be my active, this was active, this was cutoff, and this was sort of edge of saturation. We started with saturation from here, and this was EOS, or the edge of saturation, where you have a negative cutoff with you. So, this is your input and this is your output, right. So, this was the active region, this is the active region, and this is the edge of saturation. So, I get this is approximately 0.2 to 0.3 voltage VCE SAT. So, VCE SAT is approximately equals to 0.2 to 0.3 volts, fine. With this knowledge, I say that IC SAT, which is the saturated collector current, will be equals to VCC, right, minus VCE SAT by RC, fine, which means that it is basically VCC minus VCE SAT minus RC. VCE SAT will be typically very small, 0.3 maybe. So, I get VCC. So, if you look at edge of saturation minus 0.3 divided by RC, right, I get VCC minus 0.3 divided by RC, and therefore, I get VCE SAT approximately, if I say 0.2, I get beta forced is equal to IC SAT by IB, and IB equals to IC by beta IB. So, that is very straightforward looking at it, but I wanted to make it clear that one important point here, that therefore, IC, if you remember, is nothing but VCC minus VC SAT, remember, divided by RB base current, right, RB no RC, I think, sorry, RC, right. Now, so the obvious question asked is how can you maximize IC, because then only get large currents, is that you make this was as close to 0 as possible, right. So, typically the maximum value of IC will be VCC by RC, fine, that is the maximum value of. So, IC max can be written as VCC by RC, right, and that is the reason you always get, for example, in this case when you have to have a switch, you have to ensure that the current actually moves from the IC value moves from a relatively high value to relatively low values when you move from active region to edge of saturation. In the edge of saturation, the value will be relatively very small, right. So, this is you have to keep in mind as far as switching is concerned, or switching understanding switching is concerned. We now come to what is an important terminology. We use it in bipolar technology, and that is known as an Ebers Moll model, right. It is known as Ebers Moll model, also referred to as EMM or EM model, right, EM model. So, by two scientists, Ebers and Molls. The Ebers Moll model is a large signal model for BJT. Unlike the previous models, which is T and pi, this is basically a large signal, which means that we do not restrict ourselves to small changes in the input, but we are looking into large changes in the input and then trying to predict the output voltage or current from this EM model. This EM model is basically a low frequency. So, it is not even high frequency model, it is a low frequency model, and what it does is that it takes care of BJT as a two junction device. So, it is EB and CB device. So, I have got two junctions, emitter base and collector base junction, right. Therefore, what the idea of Ebers Moll was that therefore, everything can be broken down into set of two currents, one current flowing through emitter base, another flowing through collector and base, right. This is two things, and also two other component which depends on the emitter base junction and collector base junction. So, and he therefore told that the total terminal currents IC, IB and IE it will be a weighted sum or superposition of these two junction currents, EB junction and CB junction. So, that is what we are saying, that the Ebers Moll equation is that IE and IC are described by resembling a diode relationship plus the coupling between the properties of emitter and collector, right. So, this is the reason why we do an Ebers Moll model as such. Let us see how a Ebers Moll model looks like, right. Now, look at the, so this is again it behaves like a 3 terminal device. I have a base, I have a collector and I have an emitter here, E right, an emitter here, and so it is basically again as I discussed with you, it is a 3 terminal device. Now, I have current IB flowing into the base, collector IE and IE. So, it is basically an NPN transistor design which we are trying to do. Now, as you enter this point, this side is emitter, right, and this is collector. So, this is emitter and this is collector, right. Now, if you look very carefully, this is basically emitter base junction, this one, and this is collector base junction, right. Emitter base junction is defined by a diode, right, whose one side, the P side is connected to base because it is NPN. So, this is base. So, this will be diode equation, right, and as a result you will get a DE. So, why we get IDE here, I will just show you why we get it. So, if you plot a NPN, right, NPN, and if you look from this side, from the base side, right, then it will be, if you want to forward bias it, it will be something like this, right, and that is the reason we are showing you that by this statement here. So, this is the reason we see IDE here and base to collector is shown in this manner. So, because it is an NPN, so the diode will be in this direction and it will be in this direction, that is what you are seeing, right. So, both P are connected towards base and both N connected toward collector and emitter. What is alpha F into ID, right, alpha F into IDE is emitter current. So, IDE is this one emitter current which you see. If you multiply this with alpha, you get a, so remember alpha was equals to IC by IE, fine. So, I can define IC to be equals to alpha IE, that is what we have done. So, alpha F forward current multiply IE means IDE, right. So, this you multiply with this one, you get this, and similarly alpha into IDC will give you the value of collector current, right. So, I therefore see, you see the direction of the collector current is also, and the emitter current is also shown in this manner and this manner, right, and you can predict the reason why is it like that for all practical purposes. So, I get from here IE, which is looking from this side, IE equals to IDE, which is, so IE is this side, IDE is this side, and since IDC is in the opposite direction, I get minus alpha r times IDC. Alpha r is basically your this thing, reverse current gain, right, and IC will be equals to minus IDC plus alpha f into IDE. Minus IDC because the direction of current is reverse. Therefore, I can finally find out, since IE equals to IB plus IC, IB will be 1 minus alpha f IDE plus 1 minus alpha r into IDC. Fine. So, this is the value of IB which he gets as such. So, therefore, if you say alpha f and alpha r both are equals to 1, then IB equals to 0, and therefore, IC equals to I. Fine, but this is not true because alpha f, which is the forward gain, and alpha r, which is the reverse gain, will never be equal to each other. There will be a large difference between the two, and therefore, this inequality that IB equals to 0 will not hold good, right, and that is almost a sure certain sort of a network. So, using that network which we just now saw, we can write down the basic equations of Ebers Moll model. The first equation is, of course, as we have discussed, this one, which is IDE equals to ISC, VBE e to the power VBE by VT minus 1, IDC is equals to ISC to the power VBC by VT minus 1. Then IE, if you look very closely, this is basically your is IDE, right, and therefore, I get this minus this, right, IS, and then I get this minus this, we get then beta f forward and resistance and negative resistance beta r, and then we get from these equations the value of IE, IB and IC, right. And we see that if you look very carefully here, that base to collector junction is always in a forward active region. VBC will be quite large and negative, right. As a result, this will all vanish. So, I will be only left with minus plus IS. Fine. So, IS by alpha plus IS. So, I will get IS common. So, I will get IS common, right. I get 1 by alpha multiplied by e to the power VBE by VT minus 1, right. We can get like this, something like this for our understanding purposes. Same thing happens if you take negative value for your Ebers Moll model. Okay. So, we have therefore understood the basic fundamental principles of the Ebers Moll model. We have also understood how the Ebers Moll model work. We have also understood how does a BJT bipolar transducer can be removed and we can replace it by its corresponding model file, and provided we are able to sustain these equations within the model, right, and we are able to achieve a sustained value of these model files. Before we move forward to inverse and this thing, let me give you a Ebers Moll model for NPN and PNP transistor, Ebers Moll model for NPN and PNP. So, if this is basically a PNP, right, this is PNP, this is basically an NPN, right. NPN is relatively easy to handle, so I can do it. IE is equals to IF plus alpha I IR, right, and similarly IC can be written as alpha and IF minus of, because this is reverse bias, minus IR, right, because in negative side there is no gain which is available at this transistor at NPN, but for PNP you do have a gain available, and therefore, this comes out to be like this, right, and I get alpha IF plus alpha IR as the value of the base collector current, right. Now, we have also already discussed transistor operating in normal mode or forward active mode. Just to give you a brief insight what will happen in reality, we will see that as I discussed with you, that the minority current carrier will actually go down linearly from emitter base to collector base, and it will go to such a low value at almost near this thing will go to 0, because the collector will be removing all the electrons from the junction, and as a result this will go to 0. So, that is quite difficult, but since You do have recombination in the base side, therefore, this will ideally will not be a straight line, but will be slightly bend in this manner, and as a result because of the recombination, and as a result you will have bending parameter there. So, this so if you see at this model, this one, it is emitter base collector. So, in the emitter base collector, this VEB is nothing but the base to emitter forward resistance, IF is the forward current, and alpha n into IF is basically the collector current which is to be developed, or which has to be developed, right. With this idea, let me recapitulate of what we done in this module. We looked into Ebers Moll model and tried to estimate the currents for all modes of operation of BJT. Please ensure that the current will be typically very high in active region, almost 0 in the lab region, and will be moderately good near the other regions, right. So, in the saturation region, it will be typically very relatively high, but fall very fast. Active region, it will be typically very high, but remain in that high position for quite a long time until and unless an external force is pulling the node down, and cutoff is the region where the effective current is approximately equals to 0. Please take my mind, it is effective resistance and approximate resistance goes to 0. The real resistance might not even go to 0 at any point of time. So, as I discussed with you, Ebers Moll model is an elegant way of expressing a circuit, right. And then what we have neglected in Ebers Moll is we have neglected the effective base width model, right. So, please keep this in mind when we do the next time, we will be using the effective base width model, which means that when we remember when we are reverse biasing the collector base junction, the effective base width was reducing, right. So, it was going down, and as a result there were certain issues which were formed out, which were not addressed by the Ebers Moll model, right. And therefore, all your second order effects and everything which is emanating from Ebers Moll model need to be questioned, and we need to look into those facts in a detailed fashion. So, Ebers Moll model actually fails when you want to have a second order effects coming into picture, right. So, Ebers Moll model does not work very good in that case when you have second order. In that case, what works is basically my Gamal, right, Gamal-Poon's model, fine. You should look at Gamal-Poon's model, and this is much more robust model at high frequency, at very high frequency domain, right. And this is what we have learned from our previous understanding of statements, right. Okay. Okay. With this, let me also therefore we have therefore taken care of two important points in this lecture. The first point is that we have looked into transistor as the BJT as a switch. So, I can switch active to cutoff and cutoff to active vice versa by fast movement of an external peripheral source. We have also seen the Ebers Moll model and how can it be integrated with circuit analysis. We also looked into basic Gamal-Poon. Gamal-Poon will come to later on if time permits, but we have looked into those facts and we were able to sustain a much better design for a BJT based design. Okay. Thank you very much. Thank you.